am Professor Collins, and this is your daily dose of statistics. Today we're going to continue our discussion of inferential statistics, and specifically we're going to be talking about the second one of understanding inference, which is estimation procedures, and specifically confidence intervals. So let's do a quick introduction to confidence intervals. So we're going to do confidence intervals based on means, so a population mean, and we're going to do confidence intervals based on proportions or percentages. Now, what confidence intervals do, just to give you a rough idea, what confidence intervals do is oftentimes you'll hear in the news or other places that say, something like, for example, there is a 25% approval rating of the president plus or minus 3%, or with an error rate of 3%. That's exactly what confidence intervals are, right? What they do is they take a sample of individuals, use the data from that sample, so the mean and standard deviation or percentages, and utilize those to generalize to a larger population. So before we get into this, we need a few quick definitions to understand. First, what is a confidence interval? It's an estimation of the population value, also called parameter, based on sample data, in which a range of values is specified, right? So between with a top and a bottom number, between X and Y, for example. Alpha is the probability that a population does not contain the value specified. Alpha levels are typically set at 0.1, 0.05, and 0.01. These are related to the percentages, right? So if you set your alpha level at 0.1, for example, you're saying there's a 10% chance that the population does not contain the value specified. And your confidence intervals will be slightly smaller, right? 5% saying, or the opposite, you're saying there's a 90% chance that the population parameters do fit within your estimate. Same thing with the 0.05 level, right? That's 95%. 0.0 level is 99%. 0.01 level is 99%. And we'll talk more about that in a few minutes. Bias, a sample used to estimate population parameters where the mean of the sampling distribution does not equal the populations. So in this case, what it means is the sample is not well representative of the population. So we want to do our best, and think about last lecture on sampling. We want to do our best to have a non-biased sample, a sample that is random, a sample that represents the population. Efficiency is the extent to which the sample outcomes are clustered around the mean of the sampling distribution. So basically how tight our parameter estimates are, or how tight our confidence intervals are. So how large that gap is. So we'll go over several estimation procedures here. So we'll talk about some of the necessary elements. I'll give you an idea of what confidence intervals are and what they do. We'll calculate them based on population means, or to calculate the confidence intervals for population means. Also population proportion. And then I will give you an applied example of calculating confidence intervals for the population mean, not for proportions. If you want proportions, check out your textbook, or also check out some other videos as well. So first, let's talk about confidence intervals and conceptually what they mean. So say we have a population parameter, or population mean, and we don't know what that mean is, right? So as you can imagine, oftentimes this is true in the social sciences. There are very few times where we actually have the population mean. So that is unknown. And so we have our distribution here, right? We have our the shape of the distribution, we have our mean, we have our standard deviation. So this represents what the population parameter could be or probably is. However, we don't know the specific numbers of this parameter. So what we do is we use sample data, because sample data we can know the mean, we can know the standard deviation, right? So what we can do is we can use this sample data and estimate the population mean based on our sample data. So our smaller distribution down here can be used to represent the larger distribution within some given range. And so we take the sample out of the population. Then what we do is we use the sample data to then estimate the mean of the population within some range. So what are some of the necessary elements of confidence intervals? First, you need a sample mean, you need a sample standard deviation, you need the alpha level, and the alpha level determines the confidence level of the estimate. It also determines the z-score that we use in the calculation. And then you need your z-score. So let's take a look at the formulas. Now these are important, so you're going to really want to jot these down or try to remember them. So we have our formula for the estimation of population means and for population proportions. So our confidence interval for the estimation of population means is here on the left, and what we find is it's the sample mean, that's the x bar, plus or minus the z-score, which is related to the alpha level, times the sample standard deviation divided by the square root of the sample size minus 1, right? Another thing that I need to put on here that I forgot actually is one of the necessary elements is sample size. We need that. We absolutely need that, the size of the sample. So in this case, x bar is a sample mean, z is the z-score of the associated alpha level, s is your standard deviation of the sample, and n is the sample size. So you'll see a lot of the same elements here in the population proportions. So in this case, PS equals the proportion of the sample, and P sub U is the proportion of the population. And you're probably asking, well, isn't that what we're trying to calculate? And indeed, yes, it is. It is what we're trying to calculate. So what we do is we set these numbers at the most conservative as possible. So P sub U will always equal 0.5. So just keep that in mind, and we can discuss the reasoning behind that or read about it to identify the reasoning behind that. Basically, we just want to keep these as conservative. We want to keep our estimates as conservative as possible. So 0.5 maximizes that. Now let's move to calculating confidence intervals for the population mean. So we'll go through a couple of steps here on how to do this and what to do. So first we need to select our alpha level. This is our level of confidence. So this allows us to state within a particular level of confidence what our population estimates are. So for example, most statisticians use a confidence level of 95%. And so what that's saying is that 95% of all possible samples fall within the distribution, within the population distribution. There is this, and so this is also saying there's a small chance that the sample that we got actually lies outside of that population distribution, right, or outside the 95th percentile of that population distribution. And so we use this to give an idea that we're fairly confident, and the 95th percentile, the 95% is fairly confident. So what we do is we check out our alpha level, and we use that to identify the z-score. And 95% our z-score is always going to be 1.96. And so we'll use that in our calculations. So we'll calculate our operation using the equation here, as you see on the bottom right, just as a reminder. And let's run through a quick example. So first we need to calculate the lower limit. The lower limit, as you can see using the example, in this case we have, so just to clarify a little bit, in this example here we'll have a mean of 10 and a standard deviation of 1.5. So in the lower limit we have our sample mean of 10 minus our z-score of 1.96 times our standard deviation of the sample of 1.5. And then we'll have our n, or our sample size, of 100. So that's where those numbers come from, that's where those are patched in at. And we'll just follow through this with this calculation here. We'll take the square root of 99, which is 100 minus 1, and we end up with 9.95. And then we divide 1.5 by 9.95. Then we times that. Then we can times 0.15 times 1.96, which is the z-score. And after we calculate all of these numbers, what we have is 9.706. Now we calculate the upper level. And remember, we still use the same mean, standard deviation, and sample size, right? So again, our mean here is 10, which is the first number. Standard deviation is 1.5, sample size is 100. And as you can see, these calculations look pretty much identical. What we're doing is we're essentially calculating everything to the right of the plus sign in this case. And we end up here with 10.294. So we can shorten this a little bit and actually do the entire calculation and then just do that last step with a plus or minus. And you'll see me doing that with the final example. And so what we see here is with a sample mean of 10, standard deviation of 1.5, and a sample size of 100, with 95% confidence I can say that the estimate for the population would fall somewhere between 9.706 and 10.294. And what that means is the mean for the population falls within that range. That is not to say that everybody in the population their score falls within that range. What that's saying is the mean of the entire population falls within that range. You still have the variability among everybody in that population. So now let's go over to calculating some confidence intervals, specifically for the population proportion, trying to identify population proportion. And so again, step one, we do the same thing, right? We select our alpha level, and then we find our associated z-score. In this case, I'm still going to use a 95% confidence level. This is what I will use throughout most of these lectures. And then we'll calculate the operation using the equation. And so again, as a reminder, here's our equation here in the right corner. And let's take a quick example. So in this case, our example, we are going to have a population mean of, or excuse me, a proportion of 30% or 0.3. Now in this case, we don't have a mean and standard deviation, right? Because we're looking at something on a nominal or ordinal type of scale, right? Where we actually don't have a mean. What we have here is a proportion. Proportion is something like somebody saying yes versus somebody saying no, or percentage of men versus women, right? So that's what we're looking at here. And so in this case, we calculate our lower limit, right? So again, on the left-hand side here of the equation, we have 0.3. That represents 30% of the population, or excuse me, 30% of our sample. We have our z-score of 1.96, and then we have that weird p sub u, and again we're setting that at 0.5. And again, that is just to enhance it's to be a little more conservative with these estimates. And then we have our sample size of 200. Then we just continue to calculate this out, and we will end up with a final score of 0.8 or 8%. Or excuse me, 22%. And so we do the same thing on the upper limit. And as you can see, it's very similar to calculating the score for sample mean, right? We're just using slightly different numbers and a slightly different equation, but we can still calculate everything on the right-hand side of the plus sign and follow it all the way through. So this last equation is exactly like the last equation on the lower limit, except a plus there, we have a minus, right? So it's just a little shortcut you can take. So we have 0.38 or 30%. And so what this is telling me is I'm 95% confident that the proportion of people in the population ranges somewhere between 22 and 38%. And so it's whatever characteristic that may be, right? Let's say maybe 22 to 38% of people who consider themselves to be Republican, for example, right? So this is something that we can use based on a sample to estimate those proportions. So now let's move on to take a look at an applied example of this. So say I'm really interested in basketball, and I'm specifically interested in the Pac-12 conference. And one of the things I'm interested in is the height of the players in the Pac-12. So what I do is I sample UW students, Washington students, and student athletes, and I use the basketball team's height to calculate my confidence intervals. Now, just note that this is a convenience sample and this is non-random, so this may actually be a biased sample. But for the sake of this exercise, let's just assume that this is not a biased sample and this actually represents all of Pac-12. And so what we're doing here is we're using the UW players to estimate the height of all Pac-12 players, right? Or estimate the average height of all Pac-12 players. Again, this is not to say that all Pac-12 players will fall within this range, but what it's saying is the average height of all of the players, so all of them put together, will be within this range. And so step one, we need to identify our confidence level. And so again, I'm going to use the 95% confidence level with a z-score of 1.96. This will help me calculate my confidence intervals. Step two, we need to calculate the upper and lower levels. And so what we have here, so for our sample mean, so the average height of Washington players is 78.2 inches with a sample standard deviation of 3.67. Now, just a side note, this is actually real data. I found this on the internet. And so this is the listed height of the UW team. And so here is our calculation or our equation. And so let's jump into this. So what we have is, again, we have our sample mean in front, our z-score plus or minus our z-score, times the sample standard deviation divided by the sample size minus 1, right? So our sample size here is 15. There's 15 listed basketball players on the University of Washington team. So we continue to calculate this out. The square root of the sample size minus 1 is 3.74. And we divide the standard deviation by that, and we get 0.98. And then we times that by the z-score, right? 1.96. And what we come up with is 78.2, again, the mean, plus or minus 1.923. And so our lower limit here is we take the sample height, the sample mean height, and minus that by your 1.923, and we get 76.277 inches. And then our upper limit, we get 80.123 inches. So what this is telling me is that I can be 95% confident based on my sample of UW basketball players that the average height for players in the Pac-12 conference is going to be somewhere between 76.277 inches and 80.123 inches. I can be 95% confident of that. And so again, that still leaves a little bit of error, right? There's a 5% chance that Pac-12 players' height on average will be beyond that limit, right? It may be, there's a 5% chance that it'll be lower than 76.277, and there's a 5% chance that it'll be higher than 80.123. So that is our applied example here. And so we've gone through this estimation procedures for confidence intervals. We've talked about a few definitions here. And so again, this is still going to build, and so we're still climbing this mountain, right? So we need to continue storing all of this information as we climb up and get further into this into these lectures. And so next time we'll be talking about hypothesis testing for one sample case, and we'll continue our discussions on inferential statistics. And that is your daily dose of statistics.